Hello everyone, my name is Akash and this is a presentation on parameterizable LMS adaptive filters, which is a part of my final project submission for the course EE278, which is Advanced Digital Design for DSP and Communication at San Jose State University under the guidance of Professor Chang Choo. So here we go. So first of all, there is basic linear filters, which are classified by the relationship of an input and output, which is linear function. There are two types of design method: classical and optimal filter design. The classical approach generally used for low pass, band pass, notch filters, and optimal filter design is used for mostly minimizing the square value of the error signal. So adaptive filter is our main focus of control. As can be seen from the slides, the adaptive filter is basically a digital filter only. The only difference is that it has the ability to change the value of coefficients in order to optimize the system performance. So even if the environment of the adaptive filter is changing, it converges to a certain value, and hence the value of the coefficients are really adaptable to the continuously changing environment. So it is a digital filter, but in addition to a digital filtering, it also uses the adaptation algorithm, which helps it to change the value of the coefficients. So next. So here is the basic structure of LMS adaptive filter. As can be seen from the figure, it is basically a digital filter only. The extra circuitry is there for controlling the value of the coefficients, that is the filter weights, which keeps changing at every new arrival of the input signal. So there are basically two processes involved in the LMS adaptive filter: a filtering process and adaptation process. Filtering process is same as that of a simple digital filter, and adaptation process, as I mentioned earlier, is the process which finds the new value of coefficients and keeps changing the value of coefficients in order to optimize the system performance according to the changing environment. So here is the basic LMS algorithm I use for my code. According to this algorithm, the updated value of the tap weight vector can be found out by adding the old value to the multiplication of the learning parameter, that is convergence rate, tap input vector, that is the output of the LMS filter, and error signal. So it is quite straightforward, and mathematically the formulas are shown. So that's how it is. So formulas are quite straightforward and easy to understand from the LMS algorithm. So I will go for the simulation that I generated from my Verilog code. So here it is. As you can see, the error signal initially diverges, but then it converges after a few hundred samples of the input signal has arrived. So error signal is basically the difference between the desired signal and filtered output, which means that the system reaches the optimized performance. So we can abstract these values from the model sim and plot it in the Matlab plotter, which is very more clear to and easy to understand. So here it is. So this is the value of the error signal and number of samples of the input. And as can be seen, the error signal converges. But the convergence of the error signal depends on the value of mu, that is convergence factor. As can be seen, the larger is the value of mu, the smaller time it takes for the filter to converge. And the smaller is the value of mu, the larger time it takes for the filter to converge. But the value of the mu can't really be beyond a certain limited window of the values. As can be seen, it affects the different value of mu affects the convergence rate of the filter. So what is the range of the value of? Here it is. It should be between 0 to 2 upon lambda maximum, and practically it should be 0 to 2 upon input signal power. So as I said, the larger value of step size increases the adaptation rate, that is faster adaptation, but it shouldn't be more larger than a certain value. It's not greater than 2 upon input signal power, otherwise the system will never converge. And it also increases the residual mean square error. So as you can see, so this was my presentation, and yeah, there are some future works that can be done, such as make the Verilog code for fully parameterizable LMS filter. So the Verilog code that I made for LMS filter is parameterizable, but if we change the number of taps in the filter, then it needs some modification. So we can improve it for that, and we can implement it on FPGA for noise cancelling algorithm, and I think there are still some errors in the rounding and saturation logic, because of which the error diverges for a little while, but it is fine as it converges eventually. So that was it. Thank you. I hope you enjoyed the video.